Have you ever tried to catch the exact moment a second begins? You look for a click, a mark, something clear, and yet time slips by without leaving edges. Now imagine stripping the scene down even further. No stars, no space, no matter, no motion. If nothing changes, does before or after still mean anything? Some physicists say time is tied to change. Others argue it's more fundamental. We'll keep our footing in simple ideas, clocks, events, and what now can honestly measure and see how far they carry us. If this kind of calm exploration fits your pace, a quick like and subscribe helps others find it too. Settle in, and let's test a bold question. Could time exist on its own, or is it born with the universe? Does time exist without the universe? The question sounds simple, because the word time sits in everyday life. You look at a clock, you wait for a meeting, you remember a birthday, and feel the gap between then and now. Under those minutes and hours is a harder layer. It asks not only what time does, but what it is, and whether it could be there when nothing else is. To begin, notice time the way you feel it. One word follows another in this audio. That flow is time as experience. There was a moment you pressed play. There is this moment now. Another one is coming. They are different, ordered, and moving forward in a way that seems natural. Often, you do not notice this flow until something breaks the pattern. A long pause, a sudden silence, a skipped beat. Then you sense time again, or its absence, like a line that becomes visible when it is bent. What are you actually holding when you say a minute has passed? You are noticing change, a change in sound, a shift in thought, air moving with your breath. Time feels tied to motion and to transformation. If nothing changed, would time still pass? Look at the room you are in. Notice your body, lying down or sitting. Your breath moves in and out. Maybe a fan hums. Maybe light moves across a wall, even if slowly. You know this is the present, yet you also know the present used to be the future and will soon be the past. The moments lean in one direction. What you are sensing is not theory. It is the way time shows up. Quiet, steady, structuring events without announcing itself. This structure supports more than schedules and memories. It supports the basic fact that anything happens at all. Imagine removing it. No ticking, no motion, no before or after. Would anything remain that could be called time? That is the path to explore. Step back from clocks and calendars and phone reminders. Ask how time works beneath the tools we use to measure it. You may have heard the phrase, time is an illusion. In science and philosophy, it does not mean your experience is false. It means time may not be as basic as it feels. One view says time is woven into the universe, not a separate stage on which events play out, but something formed with the stage itself. Music is a helpful picture here, used carefully. A song exists because notes occur in order. With one note that never changes, do you still have a song? Modern physics pushed this idea further. With general relativity, Einstein changed how we think about time. Space and time are not separate containers. They form a single geometry called space-time. Mass and energy bend this geometry. Planets, stars, buildings, even your body tells space-time how to curve. The curve then guides motion. This leads to a result that feels strange at first. Time is not the same everywhere. Near a massive object, time runs a bit slower than it does farther away. This is not just a neat idea. We can measure it. Systems like GPS correct for this difference all the time. Without that correction, your position would drift by large distances each day. In this sense, time is relative to the shape of space-time and to where you are within it. This brings us to the deeper question. If time depends on space-time, does it make sense to talk about time without a universe? If the fabric is gone, where would time live? Go back to the beginning, as described by our best models. The Big Bang is not an explosion in pre-existing space at a particular moment. It is the start of space and time as we can meaningfully describe them. In ordinary language we ask, what was before the Big Bang? But before relies on time already being there. A common analogy is direction on a sphere. There is nothing north of the North Pole. The word north stops applying. In a similar way, asking for a before that sits outside the origin of time may not have meaning. It is not that an answer is hidden. It is that the question may need a different frame. Hold on to motion again. We use change to sense the passage of time, the ticking hand, the orbiting moon, the beating heart. Suppose nothing changed anywhere. No particle moved. Every field remained fixed. Would time still exist? This is not just a puzzle for a quiet night. In some of the core equations of physics, time does not appear as a separate object in the way we expect. In certain formulations of quantum mechanics, and in the equations that describe gravity, what matters are relations between states, not a universal clock. The math links one state to another. It does not always specify a march from one to the next, yet you are experiencing a flow now, word after word. So whatever time is, it reaches into experience. One proposal says time is not fundamental, but emergent. Emergent means it arises from deeper rules when many parts interact. Water has a smooth surface, but a single molecule does not. Likewise, time as we live it may appear when systems behave in certain ways. A common piece of this idea involves entropy, a measure of disorder, or, more precisely, the number of ways a system can be arranged while keeping the big picture the same. For many systems, entropy tends to increase. This rise gives us the arrow of time, pointing from low entropy to higher entropy. On this view, the direction you feel from past to future comes from how information spreads, how heat flows, and how memories form in physical brains. If there were no processes to change states and no way to record those changes, the arrow might not exist. In a universe with no matter, no observers, and no change, time might lose its meaning. Another proposal goes the other way. It says time is basic and space emerges. In some approaches to quantum gravity, time is treated as a key part of the underlying rules, while space and geometry come out as large-scale effects. In that picture, a kind of ticking continues, even if nothing else is happening. You could have a time without fields, particles, or curved geometry. These ideas are still being worked out, and they make different predictions in regimes we cannot yet test. At present, there is no single experiment that settles the debate. Return to the guiding question. If there were no universe, no stars or particles, no fields, no geometry, would time still be there? One camp says no. Without change or relationships, the word time has no work to do. There is nothing to measure, nothing to compare. Time is the label we place on ordered events. Without events, the label falls away. Another camp says yes. Time could be a background condition that allows any universe to arise. It does not start, It simply is. Both views struggle with our limits. We only know life within a universe, not outside one. So we test ideas by their consistency and by the pieces we can measure inside this universe. This brings the subject back to you. A person is built with memory. Your sense of self relies on order. What came first, what came later, and how those facts knit together. You wake, stand, speak, and feel. Each act sits at a place along a private line you call my past. That order helps define who you are, and also when you are. It raises a careful question. What if the feeling of time comes from how memory is formed and stored? The past may be not a thing out there, but a record your brain builds using physical marks, strengthened synapses, chemical tags, traces in neural networks. If so, time might be real as lived structure for beings that can remember and forget, while in a setting with no record and no change. The concept fades. You do not have to choose a side. Let the ideas share the same space for now, and let the pace stay slow. The edges of what time is have only begun to loosen. Next, we ask how time behaves inside you, how your body and mind track it, sense it, rely on it, and what happens when they do not. Before asking whether time can exist without a universe, it helps to see how deeply time sits inside us. It feels familiar. You check the hour, you plan a meeting, you wait for a message, and feel each second stretch. These are habits built on a steady sense that something moves forward, quietly, and without a switch to stop or reverse it. What is that forward motion? Is it a real feature of the world, or a pattern built by the brain? People often picture time as a river that carries moments downstream. The image is useful, but it hides a puzzle. If time flows, what is the river made of, and what holds its banks? If time keeps everything from happening at once, what exactly does that keeping look like? To say that something happens is to say that something changes. A sound begins, a light turns on, a foot touches the ground. Change is the sign that an event took place, and those signs help you build before and after. Without change, all you would have is a still frame, no story, no direction. Yet time is not a thing you can point to. You will not find a handful of time in a box. You only see effects. A candle that burns down, a child who grows, paint that fades, a battery that drains. These are not time itself. They are processes you read through the lens of time. You say, time passed because the state of the world is different. So, perhaps time is our way of tracking change. But then, what about places where nothing seems to change? Imagine a sealed room with no sound, no motion, no ticking, no drafts of air. If you enter and later leave, you will say time passed because your watch advanced and your body chemistry moved on. But if truly nothing inside the room altered, not a molecule, not a bit of energy, would it make sense to say that time meant anything in that room? Or does time gain meaning only when something happens? Some ideas in physics lean toward this second view. In certain formulations of quantum theory, the math describes states and the chances of those states, but not a detailed list of steps that march from one instant to the next. Relations between states are front and center. A universal clock is not. In general relativity, time is not separate from space. Together, they form space-time, a single geometry that matter and energy bend. Put a heavy object in space-time, and both space and time curve around it. Because of that, time does not tick at the same rate everywhere. It runs a little slower, close to large masses, and a bit faster, far away. A watch on a high mountain runs slightly faster than the same watch at sea level. You do not feel the difference, but careful instruments can measure it. This shows that there is no single global clock. Time is local, shaped by gravity and motion. If time can stretch, bend, and even step out of some equations, maybe it is not a basic ingredient, but a higher level one. Temperature is a useful comparison. Temperature is real and measurable, but it makes sense only for many particles together. A single atom has energy, but talking about its temperature alone is not meaningful. Temperature emerges when countless particles form a system. By that analogy, time could be similar, very real and very useful, but arising from the behavior of many parts interacting. This leads to the idea of emergent time. On this view, time is not part of the deepest layer of reality. It appears when the right patterns form. A wave moving across the ocean looks like a separate thing, yet it is the joint motion of water molecules lining up in a shape. Time, as we feel it, could be a large-scale pattern that shows up when matter interacts and records differences. Another piece of the story is entropy. In thermodynamics, entropy measures how many ways a system can be arranged while keeping its big features the same. Low entropy means narrow, orderly options. High entropy means many possible arrangements. For many systems, entropy tends to rise. A neat stack of blocks, when left alone in a restless world, tends to fall into a spread of pieces. Heat flows from hot to cold and disperses. Information diffuses. This rise in entropy gives us an arrow of time, the direction we call forward. You see it when a cup falls and shatters, when milk spills and mixes, when heat escapes a pan into the air. You do not see the reverse, because the reverse would require an incredibly special rearrangement of countless parts all at once. Yet many basic equations of motion do not prefer one direction. Watch two billiard balls collide in a video played backward, and it often looks fine. The math would still work. So why does time feel one way to us? One answer is that the universe began in a very low entropy condition, and ever since, entropy has increased. That slow slide toward more possible arrangements sets the direction we experience. You do not sense entropy rising in a conscious way, but it frames your world. This framing raises another question. What if the universe had begun in high entropy? Would the arrow be weaker, different, or missing? Would time, as we use the word, still be the same? When people say time is an illusion, they often mean that the direction you feel may come from how memory and records form, not from a built-in one-way rule of nature. The brain records the past. It does not record the future. That alone can give a strong sense of direction. But even if part of the feeling is a product of memory, the processes that allow memory, physical changes in matter, energy flows, biochemical marks, are themselves grounded in thermodynamics. Human experience adds more structure. Your body carries a 24-hour cycle, the circadian rhythm, driven by molecular clocks that respond to light and regulate sleep, hormones, temperature, and alertness. You also have shorter internal timers. You can tap a beat. You can guess how long a minute lasts. You can wait your turn in a conversation and feel when to speak. These systems are not perfect. Emotion, attention, and context bend them. Time seems to speed up when you are engaged and slow down when you are bored or anxious. Under stress, minutes can feel like hours. In flow, hours can feel like minutes. During sleep, subjective time becomes thin or disappears. In dreams, it can distort. Language shapes the picture as well. Some people think of the past as in front because they can see it, with the future behind because it is hidden. Others place the future ahead and the past behind. Some imagine moving along a line. Others picture themselves still while events stream past. None of these maps is the map. Each is a tool. This variety hints that time, in human life, functions as a model, a way the brain organizes change so that you can predict, plan, and make sense of cause and effect. If time is a model that emerges from change, does that mean it is not real? A better way to put it is that time may be real as a property of systems, not a standalone substance. It is like shape, motion, or temperature, a feature that appears when matter has structure and dynamics. On that view, if there were only one unchanging state, no differences to track, no records to store, no processes to unfold, there might be nothing to call time. There are other views. Some theories treat time as fundamental even if space is not. In those ideas, time is the basic scaffold, and space, geometry, and fields appear from it at larger scales. In such a case, time could tick, even in the absence of matter or motion. But then a challenge returns. If absolutely nothing changes, what marks one moment as distinct from another? With no events, no fields, no particles, what would separate now from later? Without a physical process to count, the words begin to lose grip. It becomes like trying to define color without light. The terms still exist, but their anchor is gone. This tension pushes back toward the systems view. Maybe time needs difference to have content. Just as a melody needs more than one note, time may need more than one state. If that is right, then time and the universe arise together. That does not by itself answer whether time had a beginning or might have an end, but it frames those questions with care. To ask whether time existed before the universe may not make sense if before belongs to the very framework that began with the universe. The exploration has stretched outward into physics, quantum rules, space-time, thermodynamics, entropy, and the arrow. To understand time more fully, it also helps to turn inward, not into theory or equations, but into your own body, into the way time lives in you, measures you, and regulates you, often without your awareness. As you listen, your body is tracking time with hormones, neurons, electrical pulses, and quiet rhythms that were taking shape before you were born. You carry clocks inside you, not just one, but many. They do not tick like the ones on the wall. They oscillate, drift, pause, and reset. Yet together, they keep you in step with a world that keeps moving. The best known of these internal clocks is the circadian rhythm. It runs on a cycle of about 24 hours and is built into the biology of almost every living thing. You feel sleepy at night and more alert in the day even if you never look outside. The rhythm is not perfect, but it is steady enough to time many processes: when to release melatonin to signal night, when to raise core temperature toward morning, when to feel hunger, when to enter dream sleep. This rhythm is not just background noise. It influences how fast wounds heal, how your memory consolidates, and how well your immune system holds the line. Push it far out of sync and problems show up. People who work night shifts or cross time zones again and again report fatigue, fuzzy thinking, digestive issues, and higher long-term risks. Your body does not only exist in time, it depends on a sense of time to stay balanced. At the center of this system is a small region in the brain called the suprachiasmatic nucleus, or SCN, a cluster of cells just above where the optic nerves cross. It is often called the master clock because it helps coordinate the others. The SCN receives light signals from the eyes, especially blue-enriched morning light, and uses them to align your internal day with the Earth's day-night cycle. This light cue is your anchor to the outside world. Remove it for long enough, and your rhythm begins to drift. Even then, your body will still keep a schedule of its own, because the machinery of timekeeping lives inside the cells. It runs on proteins that build up and break down in cycles, on genes that switch on and off at predictable intervals, and on feedback loops that stabilize these cycles across tissues. Each organ has its own local timing program: the liver, the heart, the gut, the skin, yet the SCN helps pull them into the same daily pattern so the whole system works as one. Beyond the day-length clock, you also carry shorter timers that handle seconds and minutes. These are not tied to the sun. They are tied to movement, attention, and planning. When you tap your foot to music, wait for a web page to load, or take turns in a sentence, your brain is using internal timing circuits. They do not measure time in an abstract way, like a stopwatch. They generate rhythmic patterns that help coordinate actions. Prepare the next word, fire the next muscle, hold a pause, release it. These circuits are built from oscillations and networks of neurons. They can be trained by practice and shifted by context. They work well enough for daily life, but they are not clockmaker precise. Short interval timing is also elastic. Emotions stretch it. Context shapes it. Fear can make a second feel like many. Boredom can make a minute drag. High engagement can make an hour slip by with little sense of effort. This is not just a trick of memory after the fact. When your brain flags a situation as urgent, it recruits more attention and encodes more details per unit of external time. The result is a denser record. Later, that dense record feels like a longer interval. Time did not slow. Your sampling rate went up. The brain does this because finer resolution can help in danger. More detail, better choices. This reminds us that time behaves like a physical dimension in some settings and like a psychological state in others. Gravity can bend it, mood can bend it. Both can be measured, but by different tools. Memory may be the most important tool of all. Without memory, time does not just feel different, it loses structure. Imagine sitting in a room with no changes, no sounds, no lights, and your memory is wiped every few seconds. That room would not feel timeless. It would feel like nothing. Time is not only about what happens, it is about what the present can be compared to. The gap between now and just before is where order takes shape. For this reason, many conditions change the sense of time by changing memory and attention. After trauma, people may feel time fracture or slow because stress systems alter perception and storage. Certain drugs stretch or compress perceived duration by changing neural rhythms. Some neurological disorders disturb the ability to place events in sequence, making time feel jagged or suspended. In all of these cases, the universe outside has not changed its pace. The machine that interprets it has. Sleep plays a key role in this machine. It is not a break from time. It is a reset for how you handle it. During sleep, especially deep and REM sleep, the brain reorganizes memories, stabilizes what to keep, and clears what to let fade. In dreams, time can decouple from the clock. Seconds of real time can feel like an extended scene. Events can loop or jump, yet the body continues to keep its underlying rhythm. Breathing slows and regularizes. Muscles go still. Hormones cycle through their nightly program. Cells repair and replace on schedule. Even when your conscious timeline blurs, the body's clocks keep working. This gives a layered picture of time in human life. On the surface is conscious awareness, the story of now, the felt flow. Below that is memory, the ordered line that holds events together so they can be recalled and used. Below that are rhythms, chemical, biological, and neural, trying to stay in sync with one another and with the outside world. When the layers line up, the day feels smooth. When they slip out of sync, you feel it. Jet lag is a mismatch between the outside day and your internal day. Short sleep is a mismatch between the brain's need for consolidation and the schedule you keep. The result is disorientation, not just discomfort, because your sense of self depends on continuity, an unbroken thread through waking and sleeping, through earlier and now. This matters for the larger question. If there were no universe and no physical clocks, would time exist in any useful way? It depends on what we mean by exist. For people, time is not only something out there, it is also a structure the mind builds from memory, rhythm, and expectation. Remove all of those, and time does not just become hard to describe, it loses its purpose. Without records, without change to measure, the idea has no role. There is another way to test the edges. Picture a single person floating in otherwise empty space. No objects, no light, no sound, just consciousness. No sun or moon, no stars. Would that person still feel time? Likely yes, though less precisely. The person would still have a heartbeat, hunger signals, thoughts that rise and fade. They would sense unfolding even if they could not put numbers on it. Now strip away more. Imagine no senses, no memory, no awareness of thought, just raw existence without contrast. Would time mean anything there? It starts to blur. Without change, without memory, without difference, time becomes invisible. Not necessarily gone, but out of reach. The clock might exist as an idea, but there is no observer or process to read it. This points toward a relational view of time. Time may be less a substance that flows and more a description of relations, how events compare, how one follows another. Without events, there is no ordering. Without ordering, no timeline. Without a timeline, no past or future, only unbroken sameness. That leads to a wider point. Maybe the real question is whether anything can exist in a meaningful way without contrast, with only one state and nothing to set it against. Even the word is loses edges. Identity itself relies on change. You are who you are, partly because you know who you were. You measure differences. You notice updates. Memory links the pieces. Those links ride on inner clocks. The universe has its clocks: space-time, curvature, orbital periods, thermodynamic gradients. You have yours: light and sleep, attention and memory, emotion and expectation. Your brain does not just count time. It turns time into experience. Meaning enters in the way moments are arranged and used. You wake, notice, remember, plan, and act. Even standing still, you move forward because the internal record updates. With that in mind, step back out into a more abstract space and ask what happens to time when there is no motion. On the surface, the answer seems easy. You might say time still passes even if nothing looks different, because hidden motion ticks on. Ice molecules vibrate in a frozen lake. Atoms move in solids. The earth spins. The sun rises. But what if you try to imagine a scenario where everything truly stops? Not a slow scene or a paused video, but actual stillness. Every particle, every photon, every ripple, motionless. Would time still apply? This is not only a thought experiment for late hours, it goes to the core of how we define the word. If time measures change, then in the complete absence of change, the concept loses footing. You could say time is still there, but it would have no function like a ruler. In a world with no length to measure, or a scale in a world with no mass. In physics, the link between time and happenings is tight. In Newton's picture, time was absolute. It advanced at a fixed rate everywhere, no matter what. It did not care whether anything moved. In modern physics, that idea is replaced by relativity. Time is tied to motion and gravity and can speed up or slow down depending on conditions. If nothing moves and nothing interacts, time can lose meaning. Think about any clock. Mechanical clocks count the swing of a pendulum or the turn of gears. Digital clocks count oscillations in a crystal. Atomic clocks count the frequency of light emitted by atoms shifting between energy levels. In all cases, something repeats. That regular motion is the timekeeping. If you remove the motion, there is nothing to count. The clock itself may remain as an object, but as a clock, it becomes silent. Some approaches to quantum mechanics go further. In certain formulations, the equations do not include time in the usual way. What they give are correlations. If one part of a system is in this state, another part is in that state. The relations are what matter. The sense of first this, then that can be something we add when we interpret those relations at a larger scale. If this picture is right, time is less a background river and more a tool we use to describe ordered change. Cause and effect can be expressed as links in a network rather than steps on a universal stopwatch. This shifts how stillness looks. A moment without movement may not be a moment in the useful sense. If nothing changes, no sequence can be drawn. With no sequence, there is no duration to attach numbers to. You cannot say whether it lasted a second or a billion years because those labels need reference points. Timelessness, in this narrow definition, is not a special state that we travel to. It is what you get when there is perfect sameness and no records. General relativity offers a related scene in extreme gravity. Near a black hole's event horizon, the boundary beyond which nothing returns time behaves differently for different observers. If you hover just above the horizon, your own clock feels normal, but to a distant observer, your processes appear to slow, approaching a stop as you get closer to the boundary. From far away, your time nearly freezes. Now remove the mass, the curvature, and the observer. Imagine emptiness. No fields, no forces, no particles, no waves, no clocks to run, no signals to carry. Can we say time exists there? You might want to answer yes, as a pure backdrop waiting for something to happen. But what makes that statement meaningful if nothing can ever happen? Without events, saying time passes does not add information. It is like drawing a perfectly flat line that never varies. It exists as an idea, but it carries no features to grasp. Laboratories give a small window into the link between change and time by cooling systems toward absolute zero. As temperature drops, atomic motion slows. At absolute zero, unreached in practice, but approached motion would be minimized. As scientists push nearer to that limit, the processes used as clocks in those systems slow. Rates stretch. Transitions take longer. The material resists change. This does not prove that time itself slows. It shows that the measure you rely on the happening thins out. It hints that time, as we use the word in measurement, is not separate from what is happening. It is the name we give to the pattern of happening. Stillness then becomes more than a lack of motion. It is a threshold where the concept of time stops doing work, not because time vanishes as a cosmic ingredient, but because there is nothing to attach it to. Without change, the idea cannot be cashed out in observations or records. Meanwhile, you are listening now, and words are arriving in order. Even imagining perfect stillness, you do it in sequence. One thought, then the next. The mind insists on continuity. It must follow something. That might be why timelessness is so hard to hold on to in thought. Thinking is a timed activity. Neurons fire in rhythms. Networks pulse. Memories place events onto a line. You cannot leave the rhythm, even in imagination. This returns us to the body. You are built from motion. Electrical spikes, chemical gradients, cellular cycles, breaths, heartbeats. No part of you is truly still while you are alive. So, the idea of absolute stillness everywhere, for everything, feels alien. That does not make it impossible. It means we have no direct experience of it. If such a state exists, it may sit beyond anything consciousness can feel or even frame as a well-posed question. But there's something else to consider. What if the universe began in stillness? Not an explosion, not a blast, but a condition with no change at all, no motion, no growth, no light. Would that have been truly timeless, or a kind of hidden time with nothing yet to mark it? Some ideas in cosmology describe the early universe not as a bang, but as a transition, a shift out of a perfectly symmetric, changeless state into one where space and time, as we understand them, could unfold. In that starting state, there might have been no direction to point along, no events to count, no evolution to track. Then a tiny fluctuation broke the symmetry and unlocked difference. After that, everything followed. In this view, time did not begin at a neat zero on a dial. It began when change became possible. If so, there may have been no first moment in the way we picture it, only a passage from timelessness to timefulness, a quiet tilt, the smallest imbalance that lets structure start. We cannot watch that passage happen. There is no way to rewind the universe, but we can ask whether the idea of a before makes sense when time itself is part of what is forming. If motion brings time into being and perfect stillness erases it, then whatever existed before the universe, if anything did, may not fit our words for earlier and later. It may be something that does not follow the rules our brains expect. Time so far has been an internal experience and a physical measure. If time comes from change, where does the change come from in the first place? Not only in us, but in the cosmos. A tempting answer is to imagine the universe as a grand clock. A clock ticks, the universe changes. Perhaps there is a rhythm under everything, but clocks are built to divide intervals. Their gears and crystals move in steps that we chose. The universe was not designed to tell time for us. So the question becomes whether nature has a fundamental beat, a smallest unit of duration, or a global pulse that everything follows. People often point to Planck time, the tiny scale of around 10 to the power of negative 43 or 10 to the power of negative 44 seconds, because below it our familiar ideas about space and time stop working well. Quantum uncertainty grows so large that smooth geometry may lose meaning. Even so, Planck time is not a tick of a cosmic metronome. It is a boundary in our current math, a limit to what our tools can describe, not proof that the universe moves in steps that small. So does the universe evolve in frames like a film? Or is it continuous? Some interpretations of quantum mechanics suggest that time might not be fundamental at all. What we call change one thing becoming another could be a shift in the relations among quantum states. In that picture, there is no background clock that pushes the story forward. There are only patterns that we read as motion. Yet nature gives us regularities we can trust. Light has a fixed speed in vacuum. Atoms switch between energy levels at precise frequencies. Particles oscillate with stable rates. We use those reliable patterns to define our units. 1 second is set by a certain number of cycles in the light from a cesium atom. When we say the universe ticks, we really mean we have found processes that repeat so steadily that we can base a clock on them. They are references allowed by the laws, not parts of a built-in cosmic watch. There is no single second hand sweeping across the sky, no hidden countdown guiding events. Instead, we see a world that changes in ways we can measure. Galaxies form and merge. Stars ignite, live, and fade. Atoms decay with predictable statistics. Still, general relativity tells us there is no global time that all observers share. Time is part of space-time, and space-time is curved. Each path through it, a world line, has its own proper time. A person near a black hole and a person far from it can disagree on how much time passed between two shared events, and both can be correct for their paths. Time is local, shaped by gravity and motion, not handed out by a master clock. If there is no universal clock, are there any clocks at all that belong to the universe as a whole? Not clocks in the mechanical sense, but there are large-scale processes with rates we can track. Space has been expanding since the earliest times. That expansion is not a tick, but it has a pace we can model and measure. Distances between faraway galaxies grow over time, on average, and that trend gives us a kind of background rhythm. Radioactive decay is another example. An unstable nucleus has a half-life. You cannot say when one specific atom will decay, but you can say how many out of a large group will decay in a certain span. That regularity lets us build a probabilistic clock. None of these clocks are synchronized to some hidden standard. Together, though, they paint a picture of steady evolution that we can describe. Go deeper, and the meaning of what is changing becomes subtle. Many core equations do not include a special symbol for now. They relate one configuration of a system to another without picking a direction for flow. Some approaches to quantum gravity go further and remove time as a variable. The Wheeler-DeWitt equation, for example, describes allowed states of the universe without putting them in a sequence. In that view, all possible configurations exist in a kind of static landscape. There is no movement in the whole, only relations among parts. How does that fit the clear sense that we live through passing moments? One proposed answer is that time emerges from entanglement, from correlations among subsystems. If the entire closed system is taken as a whole, it may not change, but observers inside can compare parts to other parts and detect differences. Those changing relations are enough to build what we call time. This idea, related to the Page and Wooter's mechanism, says that time is not fundamental for the whole universe, but it appears for observers who cannot see everything and instead track the way one part shifts against another. On this view, the universe does not tick on its own. It allows ticking to happen within it. It contains oscillators, decays, and cycles. From these we build our clocks, physical ones, and also the mental and social clocks that govern sleep, work, and culture. Our sense of smooth, continuous flow is something we supply. We are creatures built under sunrise and sunset, heartbeat and breath. We notice cycles because they helped our ancestors survive. We lay our stories in order because memory works that way. Outside of that lens, there may be no flow in an absolute sense. The world may be a set of relations that do not require a universal beat. If that is right, our clocks are not wrong. They are local tools that organize local experience. Even so, the question remains. We keep wondering whether something out there drives the rhythm we feel inside. The way forward is to follow that felt rhythm back, not just to the rise of stars, but to the very start of expansion, the first conditions that let anything move and persist, and to ask what time looked like at the beginning. A first second sounds clear, like the crack of a starting gun. In cosmology, that first second is layered. It is not only the beginning of contents, it is the beginning of meaning for ideas like space, time, energy, matter, and the rules that connect them. And the key steps fit within a span shorter than a breath. We call it the Big Bang, although the name misleads. It was not an explosion in empty space. There was no center from which debris flew outward, no outside into which it expanded. It was space itself, stretching everywhere, the appearance of space-time as a dynamic stage. So what does a second mean in that setting? Time, as we use it, comes from sequence, but in the extreme early universe, the structures that support our usual clocks did not exist. Space stretched fiercely. Temperatures were beyond what we can produce in any lab. The rules, at least the versions we know now, were still being sorted by cooling and symmetry breaking. If we run the story backward, we reach a boundary we cannot cross with current theories. Planck time, about 10 to the power of -43 seconds after the start. Before that, our best equations clash. Quantum mechanics and general relativity do not mesh, and we lack a tested theory that unifies them. We do not know what time looked like there, or even if that phrase makes sense. Just after that boundary, within a fraction of a second, structure began to appear. At the very earliest instance, the universe was so hot and dense that stable particles could not persist. It was a seething soup where energy and particle-like excitations traded places rapidly. As expansion continued, cooling allowed the forces to separate. Gravity stood apart first, then the strong nuclear force, and later the electroweak force, split into the electromagnetic and weak forces. These shifts set the stage for everything else. Not only what matter would exist, but how it would behave. By tiny fractions of a second, quarks and gluons began to bind into protons and neutrons. By around 1 second, free-streaming neutrinos decoupled, and nuclear reactions started to lock in the simplest nuclei, especially hydrogen and helium. Full atoms would have to wait hundreds of thousands of years until the universe cooled enough for electrons to settle into orbit. But the groundwork was in place. Seen this way, The first second was not a single moment but a chain of transitions, breaking symmetries, cooling, assembling building blocks. Many models include an era of very rapid expansion, cosmic inflation at around 10 to the power of negative 36 seconds after the beginning, ending by around 10 to the power of negative 32 seconds. During inflation, distances between points grew at an extraordinary rate, faster than light can travel through space, which is allowed because it was space itself expanding. Inflation helps explain why the universe looks so uniform in every direction, and why tiny initial fluctuations seeded the later formation of galaxies. After inflation ended, energy poured into particles, and the hot, dense state we call the early universe took shape. None of these steps happened to the beat of a cosmic stopwatch. 1 second after the Big Bang is a label we assign by comparing our present-day physics with traces we can observe, patterns in the cosmic microwave background, the ratios of light elements, the behavior of particles in accelerators, and the current rate of expansion. We work backward to estimate conditions and assign times. Our definition of a second rests on atoms under calm conditions. Those calm conditions did not exist in the beginning. The ticking had not yet settled into the forms we use now. Still, the physics gives a usable outline. Before, about 10 to the power of negative 43 seconds is the unknown regime of quantum gravity. Around 10 to the power of negative 36 seconds, inflation begins. By about 10 to the power of negative 32 seconds, inflation ends, and the universe fills with energy and particles. By roughly 10 to the power of negative 6 seconds, quarks bind inside protons and neutrons. By about 1 second, neutrinos decouple, and nuclear reactions begin shaping the basic elements. Each step followed from the one before without a pause, not as frames divided by a hidden click, but as a continuous response to conditions. Cooling set the rules, interactions did the rest. Through all of this, what we call time was forming too, not something placed over the process, but a way the process could be described, comparing one state to another, linking cause to effect. In that sense, the first second was not only a beginning, it was a transformation from a condition where nothing could last to a condition where lasting patterns became possible. What set it all in motion? Why did the universe begin at all? Why then, and not at some other moment? Here, the idea of time hits a wall, because asking why then assumes a before. It treats time as already running, as if a clock were ticking in the dark, waiting for the universe to show up. Standard Big Bang models suggest otherwise. In them, time itself begins with the universe. There is no meaningful earlier. It is not that something happened before time. It is that before stops being a valid question, like asking what is south of the South Pole. So instead of asking what happened before the first second, we ask what conditions could give rise to it. Was it a quantum fluctuation? A random transition out of a state we do not yet have words for? Some models point to a quantum vacuum, the lowest energy state allowed by physics, from which a universe could tunnel into being. Others picture a multiverse, with many bubble universes budding off, each carrying its own space and its own time. In these pictures, time can be local, not global. This returns us to the idea of a first second. What does that phrase mean if time is part of the very thing that is starting? Can we call it a moment if there was no ticking until after it began? Our minds like sequences and flows, but the first second might not sit within time at all. It might be the arrival of time, yet here we are, living in a world with clocks, order, and direction. Whatever took place in that first second set the stage for everything we see today. Galaxies, atoms, oceans, languages, thoughts. It left a trace we can still read. The cosmic microwave background, faint radiation filling space, shows us the universe a few 100,000 years later, holding the pattern of tiny ripples that seeded structure. From that, we learn something precise happened. Powerful, yet balanced, allowing complexity to grow. We cannot look before it, at least not now, and perhaps not ever, but we can see what flowed from it. That tells us the first second was not empty. It held the rules and the seeds. The remaining question is what those seeds came from, and whether time, as a real flowing thing, was already there to witness it. The phrase, "before the beginning," is easy to say. It appears in myths and stories. It fits into sentences. But when we take it seriously, it slips away. If the beginning is the start of time, before does not point anywhere. It becomes a word with no target. Still, we try to use it because we live inside time. Our lives are measured in before and after, cause and effect. When we hear beginning of the universe, our instincts urge us to ask what came just prior and what pushed it into motion. That instinct may be off. It assumes the rules of time hold, even when the framework of time itself is missing. By the best current measures, the universe, including space and time, began about 13.8 billion years ago. That beginning was not a point in space. It was a moment in which space-time began to expand. There was no location it came from, no outside void it expanded into. What began was the arena itself. Asking what came before assumes that time already existed as a container waiting to be filled. But physics suggests that time and space emerged together as part of the same event. Before the beginning would mean asking about something outside time's structure. Not earlier, not later, something else. General relativity tells us space-time is geometric. It curves under mass and energy, but push to very small scales near the start, and quantum effects should matter. That is where a theory of quantum gravity would take over if we had one in hand. For now, the field is open. Quantum cosmology offers one picture. The universe came from a quantum state without time in the usual sense, a high-energy, timeless condition governed by rules we are still learning to write down. In this view, nothing happened inside time. Rather, a fluctuation or transition allowed time to appear. The universe did not explode into being, it tunneled into being. The move is more like a phase change than a blast. Another picture is the multiverse. Our universe could be one bubble among many. In eternal inflation, a field drives ongoing expansion, and bubbles like ours nucleate within it. Each bubble has its own space-time. The background may be timeless in a simple sense, or carry its own kind of time that is not continuous with ours. If so, before may refer to something real, but not on our timeline. It would be a parent process we can infer, but never enter. Even then, time might not run across layers. What looks like before from our bubble could be disconnected from after, inside it, like two rooms with no door. You can imagine them next to each other, but you cannot walk between them. Other ideas make time cyclic. The universe expands, then contracts, then expands again. Our beginning could be the rebound from a prior collapse, a bounce. Time would not start at the Big Bang. it would reset. That allows a kind of before, but near the turning point. Time may behave strangely. The flow could bend or blur. It might even drop out briefly. The math gets hard, and the meaning grows unclear. Loop quantum cosmology offers a related path. It treats space and time as quantized, made of tiny units. In some versions, the singular Big Bang is replaced by a big bounce. The universe shrinks to a small but finite size and then rebounds. Time could continue across the bounce, but governed by quantum rules, not the classical flow we are used to. These are serious models, grounded in known principles, but they reach beyond tested ground. At the edge, our concepts bend. All such attempts face the same challenge. Our language breaks at the start. Before may simply not apply, not because nothing existed, but because the kind of existence there has no time in it. Picture a condition with no change, no motion, no record, no cause and effect, not a blank void, but a state where comparison is impossible. There is no past to set against a present, because present is not defined. That could be what timelessness means. Yet something shifted. From that state, a universe emerged. Space began to stretch. Matter formed. Forces separated. Time, as we live it, took shape. From then on, events could be ordered. Clocks could tick. Histories could unfold. Before is not a place. It is a boundary, a limit on our current framework. Not because we lack imagination, but because the structure itself denies the question. Still, the question keeps returning. It draws us forward even when answers remain tentative, because it marks the edge of what we know. Before the beginning may never yield a map, but it guides us toward the borders of our models. As we walk to that border, a fresh question appears. If the beginning is where time starts, what kind of place is that? What does it mean to have a beginning with no direction, no frame, no timeline? A place without before sounds impossible. It feels like a contradiction. A story with no first page, or a road with no starting point. Yet, at the limit of time, that is exactly the kind of place to consider. Before is a word that works only when time is available. It needs order. It assumes you can stack moments in a row. If time begins with the universe, there is nothing to stack beforehand, no surface to lay the cards on. In our minds, place and time are fused. Wherever you are is also when you are. To picture a place without before is to picture location without sequence, position without order. Daily life offers no training for this. You walk through rooms, clouds drift, you remember the last hour. All of that requires change. Remove change, and even basic ideas, motion, memory, start to weaken. Physics still invites us to try. Some models of quantum gravity describe the early universe with a wave function of the universe. In those models, time does not appear in the equation. The system is static in the mathematical sense. What we interpret as time shows up when we look at relations among parts, when one part stands in a certain correlation with another. Then an internal clock can be defined using one part as a reference for the rest. In other words, time may arise from correlation, not from a deep global clock. The universe did not begin with a tick. It began with a state, a configuration that, under the right conditions, allowed time to appear within it. That initial state could have had geometry, energy, and symmetry governed by rules. But without a symmetry-breaking event, without a fluctuation to mark a difference, there would be no reason to say one moment followed another. The state simply was. Without contrast, there is no time, not even stasis. Because stasis only makes sense when set against change. The beginning is the break of symmetry, the first difference that lets sequences become meaningful. That moment was not preceded by anything inside a timeline. It is not that something happened at a time. It is that time itself began happening. A place without before, then, is not nothing. It is full of potential, but with nothing yet unfolding. Physics sometimes points to a configuration space, a timeless map of possible arrangements. Think of it as a landscape of allowed universes. Nothing on the map is marching forward. It simply exists as a set of possibilities. From within such a structure, a specific universe can emerge, not because a hand pushes it, but because the structure permits it, like a valid solution popping out of a complex equation. Once a universe exists with expanding space, interacting matter, and rising entropy, time makes sense again. Processes can run, events can be ordered, clocks can be built. But the frame they used did not exist until they did. This view changes how we think about origins. A place without before is not absence. It is a condition that contains the seed of time without being in time. We can reach for analogies, though they all fall short. A frozen image on a screen is one. When the image is static, you can describe what is there, but nothing happens. When the image comes to life, the same pixels now carry motion. The change from still to moving is like a shift from timeless to temporal. In reality, there is no screen and no frame rate. There is only a system becoming dynamic. Another analogy uses dimensions. We often picture time as a fourth dimension, like height or width. But in some approaches, time is a side effect, a result of how space and energy interact. In a place without before, dimensions could exist, fields could exist, but sequence would not. No ticking, no unfolding, no memory, only a state that can contain time once conditions allow it. This line of thought is not just wordplay. It helps link general relativity, which relies on time, with quantum mechanics, which can sometimes do without it. If we ever build a full theory that unifies them, it may need a timeless beginning, not because we prefer it, but because time may not extend all the way down. That shift affects how we think about causes. If time is not fundamental, then first cause may not be a useful idea. There may be no spark in the usual sense. There may only be a lawful condition that, under its structure, allows time and space to arise together. None of this closes the case. It does not tell us exactly what that condition was or why it exists. It does suggest that what came before the Big Bang may be the wrong kind of question. The answer might not live in time at all. It may be describable only as a background structure without direction from which time emerges. This leaves us with a quieter picture, not an explosion triggered by a hidden fuse, but a state that simply was until it wasn't. The next task is to ask how the transition happens. What breaks the symmetry? What starts the unfolding? If time is not basic but emergent, what is it emerging from? Once we admit that time may not be a container but a product, it is natural to wonder whether it has ingredients, parts that can be studied and even altered. In daily life, time does not feel like a thing. You cannot heap it into a pile or pour it into a cup. You cannot point to an object and say it is full of time, but that does not mean it isn't real. We say time passes, we measure it, we waste it. We speak as if it flows on its own. But in physics, that flow is not written into the laws. The equations allow change. They do not demand a forward march. This leaves room for a different picture. What we call time could arise from deeper processes. Motion, duration, and direction may be surface features of an inner structure, a structure with no built-in clocks that still produces what clocks measure. Temperature is a helpful guide. It feels basic. Everyone knows hot and cold. Yet temperature is not a fundamental property of a single particle. It appears when many particles jiggle together. Faster motion gives a higher temperature. Slower motion gives a lower one. One atom does not have a temperature alone. A collection does. The system gains a new, useful property because of how its parts behave. Time could work the same way. It may not exist at the tiniest scales, but once enough parts interact in the right patterns, a usable sense of time appears not as a substance added from outside, but as a property that becomes meaningful when structure reaches a certain level. This is what physicists mean by emergent time. It is not imaginary. It is real as an outcome, not as a built-in ingredient. If time is emergent, what is the fabric underneath? One idea is that space itself is discrete, built from tiny units, not smooth, but quantized knots, loops, or nodes linked in a huge network, depending on the model. In loop quantum gravity, space-time is not a stage. It is a web of relations that keeps rearranging. Those rearrangements do not occur in time. They generate what we interpret as time. In that view, time is the order of changes in the network. Each update is not located at a moment. The update is the moment. No outside metronome is needed. The system carries its own unfolding, local, relational, and slow. There is no master beat, only many small transitions that, from within, feel like a flow. Think of a flip book. From outside, you can turn the pages at any speed. From inside the story, each image follows the last, and direction appears. There is a sense of after, not because something is ticking, but because a sequence has structure. Another approach is the thermal time hypothesis. It ties time to entropy, the count of how many ways a system can be arranged, while keeping the big features the same. As entropy increases, we point and say time moves forward. That is why coffee does not leap back into a cup, and why shards of glass do not reassemble on a table. The world drifts from low entropy to high, because the high entropy states are overwhelmingly more numerous. The laws themselves are reversible. The equations work either way. The arrow we feel is set by initial conditions. The universe began in a special, low entropy state. From there, higher entropy became likely, and that likelihood is what we label as forward. In this view, time is not made of stuff. It is made of probability of options spreading and uncertainty growing as things mix and disperse, as particles scatter and information dilutes. The future is the direction in which the number of accessible microstates grows. A more abstract idea comes from quantum measurement. In quantum mechanics, a system can exist in a superposition many possibilities at once until it interacts. An interaction updates the system. Some physicists argue that time may be bound to those updates. Each time a part of the universe interacts with another, the joint state changes, and those changes form a chain. Not because a background clock moved, but because the universe writes a new line in its record. On this account, time is the ledger of updates. The basic ingredients are transitions, quantum events, thermodynamic shifts, geometric reconfigurations. Seconds and minutes are ways we humans package many such transitions for daily use. If time is made of changes, what happens when nothing changes? Does time stop, or does it continue unseen? Sometimes, nothing changing means a static condition that simply holds. But if there is truly no internal difference, no contrast to compare, then there is no way to assign a duration. Time without change becomes invisible. This matches the earlier theme. Time is not something you pour into a system. It needs differences to reveal itself. Without difference, there is no before and after to line up. No sequence, no flow. If time has parts, they are not objects you can hold. They are comparisons. They are patterns where possibilities narrow into definite outcomes. The ticking you feel may just be the sound of change happening. This points to a deeper question. If time is built from change and change follows rules, then time might be rooted in the logic of nature, a framework like a language that becomes real only once symbols connect. If so, time did not exist first. It began with the universe. It came into focus at the first split of symmetry, when states that were previously indistinguishable began to diverge. On this view, asking, "When was time born?" is the wrong shape of question. We should instead look for the shift that allowed change, the structure that permitted outcomes, the frame where transitions could occur. What kind of reality supports that frame? Can such a reality exist without anything else? If time is not a standalone entity but something that emerges from change, then measuring it needs more than a ticking device. It needs comparisons, distances, and movement between markers. That leads to a natural follow-up. Can time be measured without space? At first glance, time and space seem separable. Time tells you when, space tells you where. The closer you look, the more they fuse. Every clock depends on motion. Every duration we measure is tied to something moving somewhere. A pendulum swings, a crystal oscillates, a photon cycles, a nucleus decays. Even inside your body, your sense of how long things last comes from rhythms, heartbeats, neural pulses, breathing, all of which take place in space. You can ask how long a process lasted, but to answer, you need a reference that repeats or unfolds, and that reference extends through a dimension. Change always has a spatial footprint, even if tiny. This is not just convenience. It is woven into the rules. In relativity, space and time join into space-time. You cannot push on one without bending the other. Movement through space affects your experience of time. The faster you travel, the more your time dilates relative to someone at rest. Strong gravity stretches time as well. Mass curves space-time. Clocks run slower, deeper in its well. If there were no space, no layout for fields, no geometry, there would be nothing for time to curve with, nothing to couple to. In that framework, time is never truly alone. It is part of the geometry. Measurement itself calls for separation. To measure, you need at least two states to compare: a start and an end, a marker and a shift. Without space, where do you put the markers? You might imagine a single point vibrating internally, but even then you would be forced to describe the vibration as having a frequency, a repetition, ideas that lean on an implicit spatial structure. Otherwise, you cannot tell whether it repeated or even define what repeat means. Quantum systems, often treated as point-like, still live in fields. They have wave functions spread over regions. They are part of a larger structure. Without that structure, there is no frame for change. Without change, there is nothing to time. It is like trying to track duration. With no clock, no motion, no memory. You could insist time is passing, but you would have no way to detect it. It would be invisible not because it is false, but because there is no contrast. Some approaches to quantum gravity replace smooth space with networks of relations, graphs of nodes and links. Time there does not exist globally. It arises from how parts of the network evolve relative to each other. Crucially, those relations have a kind of spatial character. Links connect neighbors. Connectivity changes, and that changing connectivity defines both where and when in a relational sense. Remove the network, no nodes, no links, no distinctions, and time loses its scaffold, not only practically, but conceptually. Without a stage for events, now has no definition. General relativity hints at the same lesson from another angle. Flatten space completely. Remove curvature. Remove distances and volumes. Remove matter and energy. What remains? The equations can still carry a parameter you might call time, but with nothing spatial to evolve, nothing changes. The solution becomes static. You can let the parameter increase, but the state does not update. It is like pressing play on a perfectly frozen frame. In that case, time remains in the math as a label, not as a measurement tied to observation. It has no effect you can record. So, perhaps the sharper question is not, does time exist without space? But, can time be known without space? Can it play any role in a world without spatial relations? Most models suggest it cannot, at least not in a way that leads to anything we would call real. Our concept of time involves sequences and also intervals. Intervals require something to span, a beam of light, a moving object, a decaying atom. They all cross distances. Distance and duration arrive together. Take light speed, about 299,792 kilometers per second. The number is meaningless without a distance to cross. Time is defined by how long that crossing takes. Remove spatial extent, and there is nothing to measure. Even in quantum theory, events are spread. Particle positions carry uncertainty. Fields extend across regions. Probabilities live over ranges. Collapse everything to a true, dimensionless point, and talk of evolution loses its sense. Without space, you might still name a condition, a state, but not a process. Without process, there is no duration, only a single undivided state. Some ideas about the very early universe say that near the Planck scale, time and space were not separate things. Both emerged from deeper rules that describe changes in relationships, not changes in space or in time alone. Only after the universe expanded and cooled did our familiar categories split. If that is right, then asking for time without space is like asking for sound without vibration. You can define the word, but there is nothing to carry it. It cannot reach you. This also suggests our current split space on one side, a time on the other, may be a phase suited to human scales. Far above or far below those scales, both may be shadows of a more abstract structure where distance and duration are two aspects of one fabric. In that deeper view, trying to measure time without space is not strictly forbidden by logic. It is empty in practice. There is no path for the measure to follow, no markers to set apart one instant from the next, no pulse to count, no scale to attach numbers to. Without markers, time loses contrast, and without contrast, it becomes invisible. In that view, If you have two interacting subsystems, one can serve as a kind of clock for the other. You track the change in A by comparing it to B, and their correlation is what you call time. This is the relational idea. Time is not a thing outside the world. It is a pattern between parts of the world. A simple picture helps. Imagine two quantum bits. One is designated the clock, the other the system. They are entangled, meaning their properties are linked. If the clock qubit is found in one state, the system qubit is most likely in a matching state. If the clock is in the next state, the system is also shifted. You never read an absolute time. You infer when the system is by what the clock reads. Nothing is marching forward on its own. You see order because you compare. Researchers have begun to model this in the lab. They build tiny quantum clocks out of atoms or photons and use them to time the evolution of another part of the setup. The clock is not perfect because small clocks are noisy, but the idea works. As the clock cycles through its states, the system's state changes in a predictable relation. Time, in this sense, is the map of correlations. If you isolate the system so completely that it has nothing to correlate with, the usual notion of time fades. Give it a partner to compare to, and a sense of before and after returns. A related puzzle appears when you try to treat the whole universe as a single quantum system. There is, by definition, nothing outside to provide a clock. In some equations that aim at this total description, a symbol for time never shows up. The entire universe is described by a static wave function that encodes possibilities all at once. How, then, do we get a world with change? The relational answer says, split the universe conceptually into parts. Let one part be used as a reference and the other as the target. Time then reappears because you are comparing within the whole, not looking from outside it. Quantum theory adds other twists. In standard treatments, position, momentum, and energy are observables. They are operators that act on the wave function and can be measured within limits. Time is different. It enters as a parameter that orders changes but is not itself an observable. You cannot point to a device that measures time itself, the way a thermometer measures temperature. Every clock measures some regular change, a frequency, a decay, a beat. This difference hints that time may be a tool for organizing evolution, rather than a knob built into each system. There are also effects that tie time to observation in surprising ways. The quantum Zeno effect shows that rapid, repeated measurements can hold a system in place, almost freezing its change. If you keep asking a delicate system, "Are you still in your starting state?" often enough, the system tends to remain there. It is not that time stops. It is that the act of checking interferes with the normal evolution. Here again, what we call time is bound up with what can change and how we learn about it. Another key piece is decoherence, the process by which quantum possibilities turn into stable records. A small system interacting with its environment loses delicate phase relations. Instead of many overlapping options, one outcome becomes robust because the environment records it. That record is what allows memory, and memory is what anchors a sense of sequence. Some researchers call this the environment as witness. It explains why, at human scales, the world looks classical and ordered, even though, at tiny scales, it is fuzzy. Decoherence does not pick a unique outcome by itself, but it explains why outcomes, once formed, resist being undone. That resistance supports the arrow you feel. There is even direct evidence that time's rules touch quantum objects. Atomic clocks placed at slightly different heights tick at slightly different rates because gravity runs time a bit slower, lower down. This has been shown with height differences as small as centimeters. In newer experiments, atoms have been prepared in superpositions at different altitudes at the same time. The two branches of the superposition experience slightly different gravitational time dilations, and those differences can affect the interference pattern. The lesson is simple. Relativity's time dilation and quantum superposition meet, and systems carry their own local times even at the smallest scales we can probe. Another clue comes from rare violations of time reversal symmetry in particle physics. Most basic laws are T-symmetric. Reverse the movie, and the equations still work. But in certain weak interactions, tiny effects break this symmetry. Experiments with neutral kaons and B mesons show that the probabilities are not the same when you reverse time in a strict sense. This does not generate the everyday arrow. Entropy and initial conditions still dominate that. But it reminds us that time symmetry is not absolute across all processes. The universe allows slight imbalances that would look different if you ran the film backward. Causality itself takes on strange forms in quantum experiments. In a quantum switch, the order of two operations is put into a superposition. A then B and B then A happen in a combined way with no definite order set until detection. This does not produce paradoxes because no usable signal goes backward, but it shows that what happened first can be undefined for certain processes. Order can be an emergent fact set by context and measurement. If order can be indefinite at small scales, then a strict, universal timeline is not a given. It is a large-scale feature that appears when many small events are bundled into a stable story. All of this points toward a layered picture. At the base are relations, correlations among parts, network links that change, amplitudes that interfere. On top of that sits thermodynamics. Large numbers of parts mix, and entropy tends to rise from special starting conditions. On top of that sits biology and mind, systems that record, predict, and compress the world into memories. At each layer, time looks a little different. The equations at the bottom do not name a global flow. The statistics in the middle provide a direction. The brain at the top experiences a smooth stream because it stitches snapshots into a line. None of this says your experience is false. It says the experience is a construction that matches how the underlying layers behave. There are also costs to keeping time. Any clock that is precise must dissipate energy. It must interact with something and produce heat somewhere. There are bounds that link accuracy, stability, size, and energy use. Memory storage also has thermodynamic cost. Erasing a bit of information requires a minimum energy release as heat. If a sense of time relies on forming records and comparing them, then the arrow is tied not only to probability, but to the energy budget of the records themselves. Timekeeping is never free. The universe does not hand out perfect clocks without a price. Some approaches to quantum gravity try to encode all of this in the underlying structure. Causal set theory imagines space-time as a growing set of events, linked by cause and effect, like dots connected by arrows. The geometry we see is an emergent pattern of those links. Spin network approaches use graphs with edges labeled by quanta of area and volume. Changes in the graph produce the space-time we measure. In both pictures, there is no continuous stage to start with. There are only relations whose updates we call time. When the updates are dense and regular enough, a smooth geometry appears. When they thin, the geometry loses meaning. From the relational viewpoint, a clock is simply a reliable subsystem, a pendulum, a photon bouncing in a cavity, a nuclear transition. They are all little worlds whose states cycle. You use those cycles to label other changes. The more stable the clock, the more useful the labels. But perfect stability is impossible. Noise creeps in. Gravity shifts rates. Motion drags. Even the best atomic clocks drift a tiny bit. This is not a defect. It is a sign that time is not a separate entity to be captured. It is a relation to be maintained. Quantum reference frames sharpen the idea. In classical physics, a reference frame is a rigid grid. In quantum physics, the frame itself can be in superposition. You can ask how a system evolves, as seen by a clock that is uncertain in position or motion. The answers differ from one quantum frame to another, yet physical predictions agree when translated correctly. This suggests that time is not an absolute background, but a story told relative to a chosen clock. Change the clock, and you change the language, not the facts. The energy-time uncertainty relation also plays a role. It says that the more sharply you try to define a process's duration, the more spread out its energy must be, and vice versa. This is not the same as position momentum uncertainty, because time is not an operator in the usual sense, but it still limits how well you can speak about how long certain quantum processes take. Precise timing needs bandwidth in energy. Narrow energy bands make timing fuzzy. Clocks must pay in energy spread to gain in temporal sharpness. At human scales, none of this subtlety prevents you from planning a day. The web of relations is dense. The environment constantly records. Entropy increases. Clocks tick. But the lesson from small scales and deep theory is that flow is not a basic ingredient. What is basic are rules that let states relate and change, and initial conditions that select a direction in which complex structures, records, and memories can grow. The sense of a present sliding toward a future is how a mind lives inside those rules. It is also worth noting how gravity couples to rates and thus to experience. Even without exotic devices, everyday gravity leaves traces. Your head ages a tiny bit faster than your feet because it is farther from Earth's center and feels slightly weaker gravity. The difference is tiny but measurable with precise clocks. Astronauts return a hair younger or older than if they had stayed, depending on path and speed. Proper time, the time along a path through space-time, is what each world line accumulates. Two paths between the same events can lead to different totals. There is no single answer to how much time really passed, unless you say, for whom, along which path. Experiments keep pushing these ideas. Cold atom interferometers split matter waves and let them follow different routes before recombining. The resulting pattern depends on the difference in proper time along each route. Quantum simulations mimic curved spacetime in optical lattices or trapped ions, letting researchers test how clocks behave when the background changes. None of these reconstructions prove a final theory, but they stress the same theme. Time is what systems do relative to other systems. If you try to remove space entirely, the supports for these relations weaken. Without distances, you cannot define speeds, frequencies, or cycles in the usual sense. Without a layout of connections, you cannot build a network that updates. What remains may be a mathematical object, a rule that says which configurations are allowed together. Only when part of that rule takes on the role of a clock for another part do sequences appear. Only then do words like before and after find a place to land. At the macroscopic level, life turns these sequences into meaning. A plan is a set of desired changes ordered in a line. A memory is a record of past correlations. A promise points from a present state toward a goal. None of that requires a flowing substance. It requires reliable relations and the ability to store and compare them. As structures able to store and compare grew in the universe, molecules, cells, brains, the felt flow strengthened. The line from what was to what is to what might be became part of how systems like us survive. The picture that emerges keeps time and space linked by necessity, but not because they are unbreakable objects. They are linked because the relations that build one also build the other. Geometry and sequence grow together out of deeper patterns. Where there is no pattern to compare, there is no time to say. Where there is no network to span, there is no distance to measure. Put a stable pattern in place, and a local clock appears. Put many in place, and a shared order rises. Let those patterns interact with an environment that stores records, and an arrow takes hold. At small scales, order can even be indefinite. The order of two operations can lack a fixed sequence, yet when you step back and gather many such events, a dominant direction wins out because records accumulate and entropy rises. The world, in effect, chooses a coarse-grained storyline. That storyline is the one we live in, with its hours and days and ages. The equations underneath remain silent about a global flow. The silence is not a flaw. It is a sign that the flow is something made from many quiet parts acting together. From this vantage, a clock is not a window onto time itself. It is a tool that summarizes a reliable change so you can compare other changes to it. Switch clocks, and your labels change, but the relations among events do not. Slow a clock down with gravity, speed it up by moving, isolate it to protect it from noise, or entangle it with a system to make a relational timeline. In every case, time appears as the structure carried by those comparisons. What remains is to ask how deep the pattern goes and whether there is a point below which time cannot be defined at all. If there is such a point, it is not a place where a universal clock stops. It is a level where the idea of a clock has no meaning because nothing is left to compare. Above that level, as soon as there is a contrast between states, even a tiny one, there is room for a sequence. With a sequence, there is room for duration. With many sequences, there is room for an arrow. From inside those parts of the wave function, the universe seems to move. The motion is not global, it is conditional. Choose a variable that behaves smoothly, say, a large-scale geometric feature, or a heavy degree of freedom, and let it play the role of a clock. Then express the rest of the system as a function of that clock. This is internal or relational time. Nothing outside the universe is keeping score. The ordering arises because one part can be used to label changes in another. When the chosen clock is stable and weakly coupled, the description looks classical and familiar. When it is noisy or strongly entangled, the notion of time blurs. A semi-classical picture helps. Separate, slow, heavy variables. Geometry. Large aggregates from fast. Light variables. Fields. Particles. The slow sector changes gently and can serve as a reference. The fast sector evolves relative to it. In this approximation, an effective Schrödinger equation appears with respect to the slow clock, even though no external time was provided. Coherence in the slow sector is crucial. If the clock loses coherence, if it gets scrambled by interactions, the neat evolution it supports begins to fail. Time, here, is only as good as the clock-like behavior of part of the whole. Decoherence adds structure to this story. When a system interacts with an environment, quantum superpositions spread their phase information into many degrees of freedom. Interference between macroscopically distinct options is suppressed and robust pointer states emerge. Those are the states that leave stable records in the environment. Records allow sequence. If the environment redundantly stores information about an outcome across many fragments, observers can consult different fragments and agree on what happened. This redundancy is sometimes called a Darwinian selection of records. The result is a world in which histories are consistent and reversible interference is practically impossible. The arrow you live by is the growth of records and the rise of redundancy in a universe that began in a very special, low entropy condition. Consistent histories approaches take a complementary angle. Instead of single trajectories, they consider sets of coarse-grained histories that obey certain consistency conditions so that probabilities can be assigned without contradiction. Time is not a background flow. It is the ordering within a family of histories that do not interfere. Coarse graining matters. Choose too fine a grain, and interference ruins classical logic. Choose a realistic grain, and classical narratives become accurate enough for macroscopic life. Path integral ideas fit the same theme. Instead of evolving in time, a system's behavior is computed by summing amplitudes over all possible paths, weighted by their action. Time appears as a parameter in the action when you model with an external clock, but in timeless formulations, you can integrate over configurations subject to constraints. What looks like evolution can be rephrased as relations among boundary data. Provide suitable boundary conditions and an effective time unfolds. Change the boundary description, and the same physics is recast without an explicit flow. Information gives another handle. If a clock is a subsystem that produces reliable, low-noise signals correlated with other subsystems, then time is a bookkeeping of correlations. Records are physical memory bits stored in matter. Storing and erasing records has thermodynamic cost. There is a minimum heat cost to erasing a bit. Accurate clocks dissipate energy to maintain regularity. The arrow is tied to this cost. More records, more entropy production, stronger sense of direction. A cosmos that permits abundant, cheap record making will teem with arrows. One that suppresses record formation will feel thin and timeless. The notion that time is information also clarifies limits. Try to define the duration of a very short process. To improve precision, you need broader energy bandwidth, which perturbs the system. Build a clock of limited size. Quantum noise and gravitational effects limit its stability. Place a clock in strong gravity. Its rate is altered by curvature. These constraints tie the fidelity of time to energy, mass, noise, and geometry. Time is not a perfect ruler hidden in the background. It is a negotiated agreement among imperfect devices embedded in fields and gravity. Against this backdrop, the Wheeler-DeWitt picture looks less alien. A static global state can still contain substructures that serve as clocks. Motion is the emergence of ordered correlations within a timeless whole. The key requirements are a distinguished subset that behaves quasi-classically, an environment that stabilizes records, and boundary conditions that make low entropy pasts likely. Given those, local times proliferate. Given none, the torque of flow loses grip. This brings us back to the question of whether time can exist without a universe. If by universe we mean any physical structure capable of carrying records and relations, then a truly empty outside offers no foothold. Without degrees of freedom to compare, there is no internal clock to extract. At most, one could speak of an abstract ordering defined on a mathematical set, an earlier-than relation that exists in logic, not in physics. Such an ordering is not the same as physical time. Physical time needs carriers, systems that can stabilize differences and propagate correlations. Within a universe, even one stripped to near nothing, carriers can survive. A vacuum in quantum field theory is not blank. It has modes and fluctuations. Geometry can ripple as gravitational waves. In these cases, time can be attached to patterns in fields and geometry, though its concreteness depends on available records. In a heat-death scenario, the geometry may persist but lack gradients, and records may stop forming. Equations still admit a parameter we label as time, but its link to experience withers. The question, does time still exist, becomes, does anything change in a way a clock could register and a memory could store? If not, time persists mathematically, but not operationally. At the smallest scales, the carriers of time may be hidden in network updates rather than smooth flows. Causal set approaches imagine space-time as a partially ordered set of elementary events. The order is the causal relation. Counting elements gives volume. Patterns of order give geometry. There is no metric to begin with, only arrows of can influence. Growth dynamics add elements and extend the partial order. Whether that growth corresponds to a fundamental time or merely provides an emergent ordering is debated, but either way, sequence is encoded as relation, not as an external axis. Spin network and spin foam models offer a different discretization. Nodes and links carry quanta of area and volume. Foams represent transitions between networks. Before and after are labels on layers of graph updates. When many updates pile up, a continuum approximation looks like a smooth space-time with a time coordinate. What we call duration emerges from counting transitions weighted by amplitudes. If transitions halt or become indistinguishable, the notion of duration ceases to apply. Quantum reference frames highlight flexibility at the foundation. In quantum settings, the frame itself can be uncertain or entangled. Ask how a system changes, as seen by a clock, with uncertain motion. The answer differs from the view of a different clock. Transformations between quantum frames relate the descriptions without appealing to an absolute time. Physics is the invariant content across these descriptions. Time is the grammar selected by your chosen clock. Relativity folds in by linking rates to geometry. Proper time accumulates along a path through space-time. Two paths between the same events can gather different amounts. This is not an illusion. It is measured with high precision, entangling tiny clocks and sending their branches along slightly different gravitational potentials even lets interference sense the small differences in proper time. Such experiments show that locally defined times are not merely conventions. They are physical consequences of coupling between matter, motion, and curvature. Quantum causality can even be indefinite. In certain protocols, the order of operations A and B is not fixed. The process is in a superposition of A before B and B before A. There is no paradox, because no signal loops back to deliver contradictions, but it shows that order, hence time's microstructure, can be context-dependent. At larger scales, decoherence and record formation force a definite order to dominate. The world regains a single storyline, and the arrow aligns with growing entropy. The role of initial conditions cannot be overstated. The laws allow many states. The arrow needs a special one. A low entropy past gives room for entropy to rise and for records to accumulate. Without such a past, complex structures would be rare, clocks unreliable, memories scarce. In a universe launched typical, everything would be near equilibrium. With no gradients, nothing in particular would happen. The flow you feel owes its strength to living far from equilibrium in pockets where energy streams from hot stars to cold space, support cycles, work, and memory. From an information viewpoint, time can be seen as compression across differences. A good clock compresses many microscopic events into a clean, repeatable pattern. A good memory compresses a sprawling past into a stable record that can guide action. Compression requires regularity. It fails in noise. The emergence of time is tied to the emergence of compressible regularities, where patterns are too weak or too strong. Perfect sameness. Time becomes either noisy or empty. These themes point to tests. Improve clocks, and you confront limits set by quantum noise and gravity. Place clocks at different altitudes and watch them drift relative to each other. Entangle clocks and systems to build relational timelines and see how decoherence restores classical order. Simulate curved space effects in cold atom lattices and examine how local rates change. None of these decide whether time is fundamental, but all sharpen what time means operationally, a reliable correlation resource. They also outline failure modes. A clock that interacts too strongly with what at times may cease to be a good reference. A world with no redundancy cannot stabilize histories. A geometry with no gradients cannot support engines or memories. At those edges, time thins. Not because a cosmic hand turns it off, but because the structures that give it bite are gone. If time is local and internal, then many times can coexist. A pulsar's spin is a clock for its nebula. A chemical reaction is a clock for a cell. A heartbeat is a clock for a brain. GPS satellites are clocks for navigation. None is privileged by nature. Each is privileged by use. Transformations relate them, and where they disagree, relativity tells you how and why. The universality we prize seconds that match across devices is an engineered harmony built on standards tied to atomic transitions. It is not a revelation of a single cosmic second. It is the success of choosing a very stable relation as our common ruler. Return now to the frozen formalism. A static universal state can carry within it all these layered structures, networks that update, environments that record, gradients that drive, clocks that correlate. From within such regions, observers will report time, flow, and arrow. From outside, if outside were meaningful, there is only the full pattern. Asking which view is really real may be a category mistake. The global description and the local times are two levels of the same object. The global level explains why no single flow rules all. The local level explains why flows appear and guide action, where records and relations are rich. This leaves a crisp operational stance. Time is what reliable clocks measure, and reliable clocks are subsystems with repeatable dynamics embedded in environments that allow records to form. Its direction is the way in which records accumulate from a low entropy past. Its rate is local, set by geometry and motion. Its existence is not guaranteed in bare theory. It emerges when structure, contrast, and correlation cross a threshold. Where that threshold is not met, the parameter remains in equations, but the experience and utility recede. If labels are just placeholders without difference, then the key to time is contrast. Give a system a way to mark change, any reliable contrast, and before and after return. Remove all contrasts and time thins to a parameter in math with no grip on reality. This is why the end of time, if it happens, is not a cliff, but a quiet loss of structure. You do not hit a wall, you run out of markers. There are versions of this loss that come from the universe itself. Consider a cosmos that expands forever with a tiny but positive vacuum energy. Space keeps stretching, galaxies slip beyond each other's horizons. Stars burn out, black holes evaporate. What remains is a thin bath of very low energy radiation in a geometry called de Sitter space. Even that empty space is not truly empty. It has a faint horizon temperature. Tiny fluctuations still occur, but they do not build lasting structure. They are noise without memory. You can label slices of this future with a time coordinate, yet one slice looks like the next to any local observer with finite tools. Without new records, the arrow loses force. Time, operationally, becomes a background label with nothing to do. This picture raises hard questions. If fluctuations never stop, could a rare fluctuation build a brain that briefly remembers? That idea, the Boltzmann brain, tests whether we are typical in a long, thin future. Most physicists prefer a history where real structure grows from a low entropy past rather than a future filled with fake, isolated minds. The preference is not emotional. It protects explanation. A world where records come from steady growth is one where science works. It is a reminder that arrows need not only laws, but boundary conditions that make records common and stable. There is also a softer way time can fade when order saturates. Imagine a system that reaches equilibrium. Nothing macroscopic changes. In principle, if you waited for times beyond reckoning, small systems can undergo rare recurrences to states close to a prior one. But those returns are so rare that for any practical clock or memory, the system is flat. Duration without difference is not a usable kind of time. Arrows can also bend locally without breaking globally. You can lower entropy inside your freezer by spending electrical work and dumping heat into the room. The freezer's contents get more ordered, but the total entropy of freezer plus room rises. The same logic lets life build and keep records while the planet sheds heat to space. Local arrows can point uphill for a while if they are powered by larger arrows pointing downhill. No law is violated. The accounting is done over the right boundary. This connects to a classic puzzle called Loschmidt's paradox. If the laws are reversible, why does entropy ever increase? The usual answer is coarse graining. You do not track every molecule. You lump microstates into macrostates. Many more microstates look mixed than ordered, so a random walk in microstate space drifts toward mixed macrostates. That drift defines the arrow at our level. Change your coarse graining, and you change which direction looks more likely. The arrow is not an illusion, but it is a feature of description as well as dynamics. At cosmic scales, arrows might even be two-headed. Some proposals suggest a Janus point, a special low complexity state from which complexity grows in both time directions. Observers on each side think their arrow points away from the middle. neither side sees a global flow. Each sees a local past and a local future built by rising structure. This does not settle how our world began, but it shows how arrows could come from geometry and boundary conditions rather than from a law that picks a direction. Where gravity is strong, stopping can be a matter of viewpoint. Near a black hole horizon, your clock runs normally by your own measure, but far away observers see your signals slow and dim, approaching a freeze. Inside, you cross the horizon in finite proper time. Outside, nothing seems to pass the boundary. The lesson is that time can stretch to uselessness for one observer while remaining ordinary for another. What stops depends on path and geometry. Quantum theory pushes on the same theme from below. In the frozen global description, all configurations are present in one static object. Yet within that whole, local times bloom whenever subsystems can act as clocks for one another, and when environments can store records. Take those away, and the bloom closes. You still have an equation with parameters, but no observer can sort changes into a story. Even experiments at humane scales point in the same direction. Clocks at different heights tick at measurably different rates. The head ages faster than the feet by a tiny amount. Interferometers split atoms, let the branches climb slightly different gravitational potentials, then recombine them to reveal phase shifts caused by tiny time differences. In devices that put operations into a superposition of orders, the question, which happened first, has no fixed answer until measurement pins down a narrative. These are not party tricks. They show that order, rate, and even first then can be context-dependent and relational. There are boundaries to what clocks can do. A very accurate clock must use energy and will heat its environment. A very small clock suffers quantum noise. A very heavy clock, if squeezed too tight, risks becoming a black hole. These limits tie the idea of time to practical costs. Precision is never free. It is bought by energy, size, isolation, and careful engineering. This is not just an annoyance. It is a clue. If time were a hard background, perfect clocks should exist in principle. They do not. We can approach stability, but we cannot own it absolutely. Some systems go further and break time's symmetries in controlled ways. Time crystals are driven many-body systems that respond with a period different from the drive. They display a kind of order that repeats in time rather than space. They do not produce perpetual motion or free energy, and they do not violate thermodynamics. But they show that complex matter can organize not only in space but in rhythms. The pattern still depends on drive and dissipation. It is not a fundamental clock. It is another case where relations among parts set a time, not a time that commands the parts. Cosmic horizons add a final twist. In a universe with accelerated expansion, each observer has a horizon beyond which events cannot be seen or influenced. Information is lost to that horizon in practice, even if not in principle. That loss acts like a permanent coarse graining, sealing off records and helping an arrow persist. What you cannot access, you cannot reverse. Horizon physics makes the arrow feel more absolute, not because the laws favor a direction, but because the universe's layout hides enough of itself to make reversal functionally impossible. When people ask what happens if the arrow breaks, they often mix two questions. One is physical. Can the world reach a regime where records stop forming and gradients vanish? The other is experiential. What would it feel like? The physical answer points to heat death or to stagnant patches, where dynamics slow and structure cannot grow. The experiential answer is emptiness, but not as a mood, rather the lack of any process that could be felt at all. Without new records, there is no now to stitch to a then. Even the idea of stillness dissolves, because stillness is defined against possible motion. None of this means change is fragile today. We live inside steep gradients with stars pouring energy into space. Our planet radiates heat, weather cycles churn, chemistry builds and breaks, and brains store histories at high cost. The arrow is thick here. Records form abundantly, but seeing how it might thin clarifies what sustains it. Low entropy starts, open systems, energy flow, environments that witness and remember. If time is conditional in this way, then it also suggests how different times can coexist. A chemical oscillator sets a pace for a cell. A heartbeat sets a pace for a brain. A pulsar sets a pace for a nebula. GPS satellites set a pace for navigation. None is the master. They agree only because we design standards and apply corrections for motion and gravity. The harmony is built, not given. Change the use, and a different clock becomes the right one. This layered view fits the equations that forget time. A full description can be timeless and still generate many local times when read the right way. Each local time is a perspective, not a trick, grounded in real correlations and real records. The arrow is not an axiom. It is a record of a fall from a special beginning toward more likely states, amplified by horizons, noise, and loss of access to fine detail. There are edge cases where direction could look strange. In small, carefully prepared systems, you can watch entropy dip for a short while, just by chance. Tiny movies can briefly rewind. Nothing deep fails. Statistics allow it. The point is that arrows are statistical. They rule large aggregates over long spans. At modest scales, the arrow can wobble. At huge scales, if the universe ever exhausts its gradients, the arrow can fade. Picturing all states at once, as a landscape, can make this feel cold. If everything just is, where does lived time fit? It fits as the path, carved by records, in a structure that allows them. You do not watch an external flow. You write a line through configuration space as your body builds and updates memory using energy from gradients. That line has a direction because records accumulate in one sense and not the other. It ends if records stop or become impossible to form. Seen this way, beginnings and endings are not mirror images. A beginning is the rise of contrasts, the first reliable differences. An ending, if it comes, is not a final switch flipped to off, but the loss of contrasts until labels float unanchored. Equations continue to accept a parameter called time. Experience loses a handle on it. What remains is a geometry that could host clocks if clocks could exist, and a logic that could order states if states could differ. With these pieces in place, the remaining task is to keep asking where the structure that supports time comes from and how it fails. Look for the mechanisms that stabilize clocks and records. Look for the limits that erase them. Trace how arrows can split and merge across scales. Track how horizons hide information and why low entropy starts occur at all. The answers will not add a flowing substance to the laws. They will sharpen the picture of how a world that is, all at once in theory, becomes a world that is lived, one marked difference at a time. If time ends, what is left? Physically, when no changes remain, a system settles into a static, uniform state. Experientially, when memory, contrast, and structure are gone, there is nothing to notice and nothing to report, not even a sense of waiting. From the inside, that absence would not feel like anything at all. This points to a final possibility. The end of time is not an edge you hit, but a quiet zone where nothing new occurs, no distinctions arise, and no measures apply a place beyond arrows and clocks. The universe does not halt because such a zone is reached. It simply becomes silent. Whether that silence would last a second, a trillion years, or an unbounded duration, no one could tell, because telling needs differences that are no longer there. In that silence, the story of time as we live it concludes. From there, we can turn to endings on cosmic scales. If time can fade, then the universe can end in more than one way, and each path treats time differently. In a heat-death future, the universe expands forever. Galaxies drift out of sight, stars burn out, black holes evaporate, and matter slowly decays. Energy gradients vanish. With no free energy to drive processes, no large-scale structure persists. In that version, time continues in the equations. The metric keeps stretching, coordinates keep increasing. But for any observer, if one could exist, nothing happens. No events to mark, no clocks to compare. Time becomes there but silent, a label without content. Another scenario is the Big Rip. Cosmic acceleration grows without bound until galaxies, stars, planets, and finally atoms are torn apart. If the stress on space-time itself becomes extreme enough, the rules that define structure break. Beyond that cutoff, our descriptions fail. Even if some notion of duration remained, it would be impossible to track. Duration needs processes, and processes need coherence. When coherence is shredded, time cannot be traced. In a big crunch, expansion reverses and the universe contracts. Structures collapse, temperatures climb, densities rise, events still unfold, but toward ever tighter, hotter conditions. Time does not flip direction. The sequence remains, only its shape changes. At the final singular point, if a singularity truly forms, our theories stop. In cyclic models, that collapse is a bounce. A new expansion follows. If so, time does not end, it resets. The new era would not preserve your history. It would be a fresh timeline, not a continuation. Vacuum decay sketches a sharper end. If our vacuum is only metastable, a lower energy vacuum could appear by quantum tunneling. A bubble of the truer vacuum would expand at near light speed, changing the constants and interactions inside it. For anything encountered, the transition would be instantaneous, no warning, no time to respond. Inside the bubble, a new physics would hold. That region might still have time, but not ours, and perhaps not any structure that lets before and after be used in a familiar way. These endings disagree on details, yet share a theme. The status of time depends on structure. Physical time, as it appears in our best models, does not require observers. Coordinates can continue even if no one remains to read them. But if a universe becomes so uniform and uneventful that no differences form, time becomes impossible to detect. Not because it has vanished from the math, but because there is nothing to compare. You can still number slices. You cannot tell them apart. It is like writing dates on blank pages. The numbers advance, but the content does not. That is close to a post-time reality. not an end of time, but a state beyond its use. No clocks, no records, no changes, only a background that cannot be measured because nothing remains to do the measuring. Time could persist as a coordinate, inactive and unattached. Or the concept could simply lose relevance. If the final condition is not only empty of content, but undefined in rule, no fields, no geometry, no lawful behavior, then even the idea of time loses footing. The end is not a wall, it is a fade, a tapering of what time can do. Distinctions collapse until nothing separates one slice from another. What remains depends on what time is. If time is a frame, it might persist without use. If time is a function built from difference, then when differences die, time dissolves with them. That leads to a personal turn. Where are we in this? If the universe ends, what is time to you? Strip away all external clocks, all events, all signals. Would time still exist? If it did, would it survive only where the last comparisons remain in a mind? Memory shapes your sense of time, not because it files the past like a hard drive, but because it assembles a path through change. Without memory, there is no sequence. You might see motion or hear a sound, but those inputs would not connect. Experience would collapse into isolated frames. Memory creates continuity by linking and ordering states. What came first, what followed, and what followed after that. That ordering is the skeleton of narrative, a before, a now, and a later. This narrative does not come from equations. It comes from patterns in a brain. Neurologically, memory is physical change. When something new happens, networks in the brain adjust. Synapses strengthen or weaken. Activity leaves traces. Over time, those traces let your brain reconstruct enough of what happened to hold a shape. Your felt time lives in that shape. The sensation that now slides forward may come not from an outer flow, but from constant updating of inner records. The present is always being compared with a recent stack of states. That comparison creates a sense of motion in awareness. This system can stall under trauma, sleep, anesthesia, or certain neurological conditions. Memory updates can pause. The world continues. Your inner record does not. When you return, there is no sense of how long you were gone. The tie between time and memory shows itself, not just as a tool for measurement, but as a requirement for presence. There is also an asymmetry you cannot ignore. You remember the past, not the future, though in some physical pictures the future is as fixed as the past. Memory does not read files from space-time. It records traces left by events. This direction from event to trace to storage is why you cannot remember what has not occurred. It is also why each act of remembering changes the trace. Recall is not passive. Retrieval rewrites. Your personal timeline is a construction that is always being edited. Even now, your memory is holding a word, connecting it to the next, building expectations, registering change. Those operations give you a sense that this moment is happening now, rather than before. But what if there were nothing left to record? In a final, featureless cosmos, no motion, no contrast, no signals, the brain, if it somehow still existed, would receive nothing. Memory would stop updating. Awareness would shrink. Now would lose shape. Personal time would dissolve. This does not make physical time unreal. It suggests that the version of time that matters to you, the one with weight direction, and meaning comes from remembered change. Your sense of self is bound to that. You feel continuous because memory links moments. You feel different from your past self because differences were recorded. In this sense, a mind is a kind of clock. It does not tick evenly. It integrates changes into a running record. When memory is disrupted, time distorts. Moments stretch or compress. Events lose order. The arrow wavers. The lesson is that much of what you call time is built from internal structure, not from the cosmos alone, but from neural processes shaped by it. So, when asking whether time continues after the universe ends, part of the answer depends on whether anyone remains to remember. Without memory, time loses shape. Without shape, it becomes something else. An unmarked backdrop, not a path. If memory gives time meaning, then minds are part of how time becomes real, not only by noticing it, but by holding it. Follow this to its edge, and another idea appears. Through many layers, equations, particles, clocks, stars, time looks like something external, a scaffold the world sits on. Strip away tools and systems, and you find a stranger possibility. Maybe time is not something you pass through. Maybe it is something you generate. Your body is a physical system in thermodynamics on a spinning planet. You age because cells change. You move through time because the world around you changes. But from the inside, the experience is different. You do not simply see time, you carry it. You remember what just happened and anticipate what might. You track sequences and sustain a sense of now that seems to move, not in steps, but in awareness. Awareness is part of the world, not outside it. Yet it is not reducible to a clock's ticks. It assembles. It builds time from contrast, memory, change, and attention. You wake and already know the order of things, not because you checked a stamp, but because your mind maintains a story that unfolds. That story has an arrow, not a physical arrow, but a constructed one, a path through mental states. Each moment, your brain receives new information, integrates it, decides what to keep and how to arrange it. In doing so, it defines time not universally, but personally. Two people do not feel time the same. No two memories align perfectly. That is not a bug. It is what it means for time to live within a person rather than only around them. When your state changes illness, fear, deep focus, time bends. It expands or tightens. The outside world continues, but your internal measure can drift. That drift is a clue that what you call time is not simply out there, waiting to be felt. It is also in here, shaped by how you process change. Thoughts do not merely unfold on a timeline, they help make one. Attention does not simply follow time, it shapes the feeling of its motion. Memory is not only a record, it is the glue that gives direction to a life. Now return to the question of endings. If the universe's structures fail, if clocks break, and if processes end, where does time go? Part of the answer is, it goes with the last structures able to compare. If nothing remains to hold differences, time is a list with no entries, a line with no points. It can be definable in principle, yet empty in practice. If time emerges from difference, and difference is perceived through awareness, then the time you know is inseparable from consciousness, not because the universe depends on you, but because your sense of reality depends on time, and your sense of time depends on how you live. You are not outside time, but neither are you only inside a fixed flow. You assemble time from how your mind handles the world. When thoughts pause, when memories quiet, when awareness lets go, time softens. Not because the cosmos has changed, but because the version of time that mattered most, the one you felt and carried, has gone still. With this in mind, the earlier questions align. Can time exist without matter? Equations say yes. Experience says only if there are structures that change and can be compared. Can time exist without space? Not in any usable way. Clocks need relations and paths. Can time exist without observers? As a coordinate, yes. As lived, no. Is the arrow fundamental? The laws do not pick a direction. Arrows come from low entropy beginnings, record formation, and loss of information to horizons and environments. Can time end? It can cease to function when structure, contrast, and memory vanish. What remains then is either a bare parameter with nothing to label, or the end of the concept itself, if rule and geometry fail. Across all these layers, a single thread is enough to hold the picture. Time is the structure that differences trace. Where differences grow, time thickens into experience. Where they stabilize, time becomes regular and measurable. Where they fade, time thins to a label. Where they are absent, time is undefined. That is as true for a cosmos approaching heat death as it is for a mind drifting out of awareness. In both, the same link breaks: comparison. And so the last step of the story does not search for a hidden river flowing beneath reality. It looks for the conditions that allow reliable differences to arise and persist laws that admit structures, boundaries that let records form, energies that drive cycles, geometries that shape rates, and minds that bind moments into meaning. Where those conditions hold, time appears. Where they do not, time is quiet. Maybe time was never a freestanding thing. Maybe it was always a relation, a sequence built from remembered change. Maybe time is what the world looks like when you are paying careful attention. And at the level that matters most to a life, maybe time is you.